We're here at the example table, and in this video we're going to continue talking about graphing rational functions. In particular, we're going to graph this rational function where the degree of the numerator is greater than the degree of the denominator. As we've seen before, having the polynomials in factored form usually makes it easier to graph rational functions. But in this case, we're going to do something first that will be a lot easier if we expand both the numerator and the denominator. So I'll leave it to you to verify that the numerator, when you expand it, is 3x cubed plus 9x squared minus 75x plus 63. And the denominator is x squared minus x minus 2. Now that extra step that we're going to do here is polynomial long division. So we're going to divide the numerator by the denominator. So let's put x squared minus x minus 2 here, and we'll put 3x cubed plus 9x squared minus 75x plus 63 here. Now, x squared goes into 3x cubed 3x times. So let's put 3x here, and then we multiply 3x by each term in the denominator. So we get 3x cubed minus 3x squared minus 6x. We're going to subtract this from this. The x cubed terms cancel, and we are left with 12x squared. Remember, we are subtracting a negative 3x squared, so that's adding positive 3x squared. So you get 12x squared minus 69x. Again, we are subtracting a negative 6, so we're adding 6, then plus 63. X squared goes into 12x squared 12 times, so you get a plus 12. And we do the same thing. We'll multiply this polynomial by 12. We get 12x squared minus 12x minus 24. And we subtract. Here we get negative 57x plus 87. Now the degree here is strictly less than the degree here, so we're done. In other words, by polynomial long division, we see that f of x can be written as 3x plus 12 plus this remainder over our original denominator. So plus negative 57x plus 87 all over x plus 1 times x minus 2. Now this is going to help us graph the function, and we'll see that next. Let's just rewrite f of x in both forms. So it's 3 times x minus 1 times x plus 7 times x minus 3 all over x plus 1 times x minus 2. And that long division showed us that this equals 3x plus 12 plus negative 57x plus 87 all over x plus 1 times x minus 2. Both of these forms are going to come in handy. So let's sketch our axes. Now let's determine where the vertical asymptotes are. We're going to look for where the denominator is 0 and the numerator isn't 0. There's neither an x plus 1 term nor an x minus 2 term in the numerator. So both times when the denominator is 0 will give us vertical asymptotes. So let's put 1 at negative 1, and we'll put 1 at positive 2. Now in previous examples we've seen horizontal asymptotes, but in this case the degree of the numerator is larger than the degree of the denominator, so we don't have some sort of cancellation going on that will lead to a nice horizontal line, like 1 over x going to 0, or x over x plus 1 going to 1 as we plug in really large values of x. The function is the same as this. So for very large values of x, this thing goes to 0 because we have a linear term over a quadratic, but we're left with this. In other words, for large values of x, this function looks like 3x plus 12. So we don't have a horizontal asymptote. In this case, we have what we call a slant asymptote. So let's sketch this slant asymptote, 3x plus 12. It's going to look something like this. And once again, this is not to scale. So let's start sketching our graph. We can find where the graph intersects the x-axis by figuring out where this numerator is 0. So it's going to be 0 at positive 1, so right here. It's going to be 0 at negative 7 and positive 3. Let's put in the positive 3 first. Negative 7, I'd like to know, I know that it's to the left of this vertical asymptote, but I want to make sure I put it on the correct side of this slant asymptote. So this slant asymptote is 3x plus 12. It's going to be 0 when x is negative 4. So negative 7 is to the left. So it's going to look something like this. So let's go back to this vertical asymptote. This is x equals negative 1. If we plug in something slightly smaller than negative 1, negative 1.01, imagine, then this is going to be negative, this is going to be positive, this is going to be negative, so the numerator is positive. This is going to be negative, and this is going to be negative. So the denominator is also positive. So as we approach this vertical asymptote from the left, we're going to go up toward positive infinity. So it's going to look something like this. We know it's going to come down, it's going to intersect here at negative 7, and then it's going to slowly approach this slant asymptote. It probably doesn't do this little curve thing here. It's what makes a sketch rough. So it's going to approach 3x plus 12 as x approaches negative infinity. Now, let's see what happens between these two vertical asymptotes. If we plug in something slightly larger than negative 1, then this is going to be negative, positive, negative. This now is going to be positive, and this is negative. So the result is a negative. So it's going to come up something like this. Where is it going to intersect along the x-axis? Well, along the y-axis, we can plug in x equals 0 to find out exactly where. But once again, what I really care about in terms of this sketch for this video is whether it's positive or negative. I can actually figure that out knowing what I already know, namely that the only x-intercept between these two asymptotes is at 1. So it can't possibly go up and intersect at a positive number. So when we evaluate this function at x equals 0, we must get a negative number. I'll leave it to you to verify that. So it must come up like this. Let's see what happens, because it could happen that it touches this point and then comes down and approaches the this vertical asymptote going toward negative infinity. So let's verify, let's determine what it does. If we plug in a value, remember this is x equals positive 2. If we plug in a value that's slightly smaller than 2, this is positive, this is positive, this is negative, this is positive, and this is negative. So we have two negatives, which make it a positive. So this is going to go up toward positive infinity. If we plug in something slightly greater than 2, these things are still positive, this is still negative, but now this is positive. So on this side of the vertical asymptote, it's going to do something like this. It's going to cross the x-axis, and then in the very long run, it's going to go up and behave like 3x plus 12.